Hello, my name is Max Smith, and I am a part of Project 19141 titled Optimization of Crema Producing Coffee. My team members are Michaela Caputo, Richie Karate, and Nate Marshall, and we are all chemical engineers. The objective of this project was to come up with a new coffee filtration method that will optimize the amount of crema and minimize the amount of grounds that will remain in the final cup of coffee. So the requirements of our system is that it has a higher performance than devices like it in the market currently. It's safe and easy to use for the consumer, as well as being cost effective for the manufacturer and the consumer. So what is espresso? As shown in the picture, it's an Italian-style coffee that has a layer of crema on top. Crema is simply an emulsion of aromatic oils in air that enhances the flavor profile of the coffee. This crema is so important for producing a great cup of espresso. So our device is called the Crema Cup, and our main task was to find a filtration method to use with the Crema Cup that will exceed the other performances of the espresso machine and current hand presses. So the main problem with espresso machines is that they're expensive, they require regular maintenance because of the high pressures and temperatures needed to produce espresso, and it also requires a lot of skill and practice to come up with a good cup of espresso from using these machines. The main problem with current hand presses is that they lose crema because of the paper filter. So our main challenge was finding a way to filter out this coffee that would get rid of the grounds and allow the crema to form on top of our espresso.
My name is Michaela Caputo, and I will be talking about the materials and testing methods that were used in our design project. So first, starting off with the materials, we used an AeroPress coffee maker, 3D printed attachment, which is what made our crema at the end. That was made from tough 2000 resin. Stainless steel mesh and slot filters of various sizes. And then we used Kirkland Guatemalan organic coffee beans from Costco, an OXO brew conical burr coffee grinder, which is used to grind the coffee beans, and then paper coffee filters, which is what we use to weigh the coffee grounds as part of our experiment. So now the testing method was identical for each test to make sure we had consistency. The only thing that varied were the sizes of the filters as well as the orientation of the filters, whether it was a single filter or two filters in series. So to start, we would weigh 15 grams of coffee beans, and then we would grind them at a setting of 6, which is about a medium grind. And while we were getting the coffee beans prepared, another team member would heat up the water in an electric water kettle. And then we would pour the grounds into the AeroPress using a filter, remove the filter, add the water to the AeroPress. After about 30 seconds, we would stir the solution, and then we would let it brew for 2 minutes. Once it was done brewing, we would push the coffee through the attachment that we made, which is our Crema Cup, and then we would pour out the finished coffee. Our final product would be a cup of espresso coffee with a top layer of crema foam. For our experiment, we needed to know how much coffee grounds were left over in the cup of coffee, since we wanted to minimize that variable. So instead of making a cup of coffee, we poured it into a water filter, let all the water drain out of it. So all we were left with were coffee grinds. And then we would stick the coffee grounds in the oven to let them dry out. And then at the end, we would weigh how much coffee grounds were left over in our cup.
For prototyping, results, and product design, you can see that we tested many filters throughout the semester in order to determine the optimum setup for our Crema optimization project. You can see here that we measured the crema volume and the percentage of grounds remains that came through the filters of different filters, including mesh filters from 20 wires per square inch to 100 wires per square inch. We also used metal filters called slot filters, where the width of those holes were actually 4 thousandths of an inch up to 10 thousandths of an inch. As you can see, the 80 mesh filter ended up producing the most crema, and the 4 thousandths of an inch slot filter minimized the amount of grounds that came through. We decided to test some of these filters in series in order to determine the optimum setup. Now, as you can see below for our product, starting from the bottom up, you see a plunger and a brewing chamber. Now, those are part of the original AeroPress design. The plunger pushes brewed coffee through the brewing chamber, up through filters housed in the filter housing above. Now, this is where our design begins. The filter housing uses a quarter-turn locking system to lock directly into the AeroPress as an attachment. The filters are housed inside and sealed off using a silicone O-ring. After the coffee is brewed and pushed up through the filtration system, it's housed in the upper chamber. Now, the upper chamber is essentially just a place to hold coffee before it's poured. However, for our prototype, we etched lines in the clear cylinder used for the upper chamber to help determine the volume of crema in each pour. We used a metal lathe to make 1 milliliter markings on the side of the upper chamber. Now, once all of the system is put together, it's very easy to press the plunger, push coffee through the filters, and create a great cup of coffee in the upper chamber.
This is an example of what Crema looks like when it's inside of the AeroPress. And as you can see here, this is how the filters sit inside of our device. Now, once the filters are inside, it's simply an easy pressing motion downward in order to preserve the crema and filter out all of the solids inside of the coffee. After pressing is complete, the crema on top is very stable and very appealing.
Throughout the last few months, our team has been running different configurations on filters for our prototype. As Nate mentioned in the graph, from our results, we concluded that the 80 mesh pre-filter in series with a 4000 slot filter gave the best preservation of crema at 4.5 milliliters and yielded the least amount of grounds to pass at only 4.85%. Pictured here are the pre-filter and the slot filter used. Below them is a picture of the product with our prototype and its configuration. In our design, we had many different characteristics from the original press methods. The first was switching from a conventional filtration to inverted filtration. This was to preserve the foam because with conventional filtration, the grounds pass through the foam as it's being pressed, therefore destroying the crema. With inverted filtration, the foam always stays atop. Next, we switched from paper filters to metal filters. Like the filtration, paper filters absorb the crema, opposite of what we want. With metal filters, the crema can be passed through without any interruption. The metal filters are also good because they can be heated up to very hot temperatures. They're reusable, they're easy to clean, and they won't leach into our product. Then the reason why we use a pre-filter in series with a slot filter is because the 80 mesh filter cycles out the more coarse grounds before the slot filter cycles out the finer particles. Using these together, only the finest particles can be passed through. We use baffles so that the hot liquid passing through the filters would not jet up like a geyser. With research and help from experts in costing for our prototype, 3 variables affect the cost, with high production tooling being the most expensive because we want the highest grade of quality possible in our product. It would cost approximately $37,500 for the injection mold for our prototype, costing 26 cents per drink for the consumer, and it would cost nearly $8 to produce our prototype. This is because we are using polypropylene in our crema cup. This is due for a few reasons. Polypropylene has a high heat tolerance, so it will never leach into our product. It is dishwasher safe, reusable, easy to clean, and BPA free. With a cost of $29.95 for each crema cup, we would see a 135% return of investment after 10 years.
We would like to thank Dr. Daniel Marshall, Dr. Adriana Brush, the Chemical Engineering Department, and everyone involved in Senior Design Day for all that they've done for us. We believe that we worked very hard throughout the semester, working with a 1 semester timeline and an even shorter timeline due to the coronavirus. We are definitely looking forward to seeing what everyone else has been able to put together. Thank you.